All right, good morning. How is everyone? All right, good morning. How is everyone today?
Doing well, Nick. How are you doing?
Doing okay, thanks. So, hope everyone had a good weekend. So, we're in week 10 out of 11. We only have class 2 days this week, Monday and Tuesday. Wednesday is a faculty work day, and then Thursday, Friday are holidays. So we'll only meet 2 days this week. And then we have 5 days next week, and that's it. That's the end of 224. So we're coming up to the end quickly. Homework 8, you've hopefully turned it in. About a fifth of the people in 224 have not turned it in. Hopefully that's none of you. And I'm not going to get to this for a few days. I'll probably get this graded sometime over Thanksgiving break. And I'll post grades once I have them. General word of advice. Since you're submitting things on Git, if there's any possibility that you did not get your code submitted, keep your Git repository intact. Because sometimes, if I try to grade your homework 8 and I don't have it, I wasn't able to download it. It may be that you didn't add me as a reporter, or you named the repository, lowercase homework 8 or something like that. If you can present your Git repository intact and it has, your log file messages showing that this was done before the deadline, sometimes that will work to get your assignment graded. So don't, turn in your code and then delete your whole Git repository just because you feel like celebrating or something, right? Keep that stuff around. That can be a useful way to validate when you had work done by. So that's just a general comment. All right. So someone asked, what is the service learning project mentioned in the syllabus? So I need to go through and clean up a few things from the syllabus. So normally, in your typically final year at Clark, you work on a project for the entire 3 quarters, called the Service Learning Project. And the idea is to pick a project that you're interested in, something you could feel passionate about, that requires you to work beyond your course learning, to pick up new skills on your own, to really kind of push the limits of your knowledge in some area that you're interested in exploring more deeply. And typically this begins in fall and then continues through winter and spring. And at the end of each quarter, there's a large expo that takes place in the STEM building where, we set up tables and people present what they've done so far, and the whole school is invited, and, typically like deans will show up. Sometimes people from industry will come by, and so on and so forth. We did not do this at the end of spring because lockdown was, in the process of happening, and we're obviously not doing it in fall quarter because we can't have that kind of gathering. So the SLP is not a part of this course. Now it's still listed as some percentage of the grade, and what I'm going to do is I'm going to give everybody full credit for that component. So that's a little bit of a grade upward curve there. Everybody's going to get 100% for the SLP piece, rather than adjusting the percentages of the other components. But starting in winter, we will talk about SLP, and that's when you'll begin it, and we'll have some kind of virtual expo at the end of winter quarter where people can present their results so far, and other people can come by and look at them, and so on and so forth. And Izad and I are trying to figure out details of what that's going to look like. So you do not have to worry about the SLP component for this fall quarter. everybody will get 100% on that component in Canvas. And then we'll talk about details of it in the start of winter term, and how to pick a project and how to proceed with it and so on and so forth. All right, cool. Other questions? So I started looking a little bit at the homework 8s before class. Um, Looks like most people did not do things the way that we talked about them in class. People are using other constructs and mechanisms and things like that, which is okay. I'm fine with that. I'm happy if people want to learn more about, other ways to do things, learn about input field separators, things like that, doing string processing in Bash, without sed, or writing full-blown awk programs or things like that. That's great. But hopefully the output is still what it's supposed to be. So I'll get these graded sometime over the coming week and get comments posted. All right, just a quick question on homework 8, an error I ran into. Yeah, go for it. During test 3, my program will give the error bad array subscript. So when you have an associative array, remember you can access it with any kind of index that you want, right? So you can say something like hash bracket hello, right? Where this index can be more or less anything. But if this is an empty string, you'll get that error saying bad array subscript. Right? So if that's happening, if you've got empty phrases coming into there, the easiest way to deal with it is just throw in an if statement. Before you use a phrase to index your array, just check to see if it's blank. And so if we call this something like key, right, you can say if key equals quote. And if you're inside a for loop where you're breaking up your space separated set of phrases, easiest way to get out of that is just use a continue statement. Continue takes you back up to the top of your innermost for loop. The alternative is to say, if your key is not blank, then read the value, increment it, write it back in, right? But just surround all that by an if to make sure that your phrase isn't blank. Yeah, you can also turn that into something to make it non-blank, as long as you suppress that in the final output and you don't accidentally suppress something that could be a valid phrase. So I think if you just turn it into an underscore, that should be safe, because the space should not be a valid phrase. So there's different ways to mitigate that. Cool. Other questions? I could not get those dollar signs to work. My test echo command showed how to do it with my final print command, but I have no idea what was wrong. Come by office hours tonight if you want, and you can show me your code, and we can try to pin that down. Because I still don't know exactly what some people are doing differently that's making that a problem. The dollar signs seem to get treated like normal characters if you have them inside quotes in the right way. But yeah, come by office hours if you can. I'd love to see your debug statements and see where those are getting getting changed. Yeah, you can definitely take a look at it. Mondays 7 to 9 at night. Wednesdays, well, there's no Wednesday or Friday hours this week, but tonight 7 to 9. I don't know if it's going to be crazy busy or totally dead. I've been getting kind of swamped by emails related to registration and plans of study, so there may be people coming in, but come by office hours, and if I don't let you in right away, you'll be in a waiting room, and I'll get to you as soon as possible. I have a feeling it's going to be really quiet. Partly because homework 8 is done, and I won't be doing any more programming assignments for this course, and I won't be doing any more ODPs. So you're pretty much done until the final exam, which doesn't mean you should like stop coming to class and stuff. But you've probably got plenty to do for your other courses over the next week and over break, and in the week before exams. So we'll concentrate on going through stuff in lecture and answering questions, but I'm not going to do any more programming assignments this course. We talk more about what's on the final, what's allowed, etc. I have not completely decided on the details of the final exam. What will be on it is probably a number of programming questions and some conceptual questions, but I haven't pinned down that mix yet, and I haven't completely decided what I'm going to do format-wise. If it's going to be a Canvas quiz or if it's going to be something different from that. I'm still thinking about it, so we'll have to talk about that the last week of class. But you can expect it to cover, all the programming concepts we've been using in ODPs and in programming assignments. And whatever Linux stuff we've been using, the most. So obviously sed and things like that. Some GDB for debugging, although we haven't done a lot with that lately. So I don't know. I haven't written it. I haven't gotten very far thinking about it yet, because this is such a different quarter from others. But we'll get to it next week. And the final, you can find the final exam schedule, and that's when the exam will be, and it will be probably a Canvas quiz, but we'll see. All right, let me talk a little bit about associative arrays. There's a little bit of discussion in Discord about faster ways to do this tallying of phrases, and some people came up with some pretty cool solutions using things like unique, which will count how many times something occurs in a file, or using grep to search a file for a string, right? And using these things, you can do homework 8 and not even have to deal with associative arrays and get faster execution. But some people are coming away with the belief that this means associative arrays are really inefficient and really slow and clunky. And I don't want you to come away with that impression, because the opposite is true. Associative arrays are one of the most efficient ways to store information in particularly a large set of data, and to retrieve it efficiently. And so I just want to really briefly introduce the concept of order of complexity. And this is something that sometimes we get to in CSE215, but I haven't for the past few years. But we will talk about this in CSE222. But this is as good a time as any to start talking about it. So order of complexity. And here's the basic idea. You have an algorithm to search, to sort, to solve some problem. How do you measure how efficient that algorithm is? And you don't really want to do it by how much time it takes, because that depends on what machine you're running on, right? What data you're passing it. If you're trying to sort 10 things or trying to sort 10 billion things, it's going to take different amounts of time. And if I run it on my laptop versus a supercomputer, it's going to take different amounts of time. So really what we study more than how long does an algorithm take is, as the problem you're solving gets more complex, how does the time increase? And so we think about these things in terms of n. So n equals the size of the problem. So let's just think about searching for something in a list, right? So you have an array of numbers or phrases or something, and you want to search for a particular phrase in there, and let's say your array has n things in it. Well, a really easy way, this is big O notation, a really easy way to search for something is just check the first thing, check the second thing, check the third thing, go through the entire collection of n pieces of data and see if any of them are the thing you're looking for. Well, if you have n pieces of data, this is going to take on the order of n operations, what we call order n. So if you have 10 pieces of data, you're going to have to do 10 comparisons. If you have 100 pieces of data, you're going to have to do 100 comparisons. Okay, the key thing about that, the more data you have, the more time it takes, but the way that time increases with respect to the size of your problem is linear. Doubling the amount of data doubles the amount of time. Quadrupling the amount of data quadruples the amount of time. And an order n algorithm can be pretty nice. Now there's other algorithms that are order n squared. An example of that is a bubble sort. So if you remember bubble sort from 121, you have a set of things that you want to put in order. You make a pass through, and at the end of the pass, your largest item is at the end of your array. And then you make a second pass, and at the end of that, your second largest item is in its correct position. You make a third pass, and you have a total of n passes, and each pass has to work on n pieces of data. So this takes approximately n squared operations. And the takeaway from that is, if you have 10 pieces of data, it's going to take you 100 operations. If you double the amount of data, you quadruple the amount of time, the amount of operations. Okay, this is the significant part. Double the amount of data, quadruple the amount of time. Triple the amount of data, the amount of time goes up by 9x. Okay, that's what the n squared is capturing. It's quadratic growth. So instead of linear, it's quadratic. There are matrix operations where you have a matrix that you want to, multiply or something that'll end up being order n cubed. Well, what does n cubed mean? It means if you increase the amount of data by 1000x, you increase the amount of time by 1,000,000,000x. And this thing that used to take a second now takes 1,000,000,000 seconds. Okay, 1,000,000,000 seconds is a really, really long time. You don't want a program to take 1,000,000,000 seconds. So this is a horrible order of efficiency. A better order of efficiency is logarithmic. Okay, this is the greener side of the fence. When your time increases by the log of n, what does that mean? If I increase the size of my data by 1,000,000, my time will go up by like 20, if this is log base 2. If I increase the size of my data by 1,000,000,000, my time it takes to run my algorithm goes up by 30. Right? So 1,000,000,000 times more data only takes 30 times longer to run. So if it used to take a second, now it takes 30 seconds. Well, that may be perfectly acceptable. So our high-low game, a binary search, that's a log n algorithm. That's why high-low is so efficient to win if you know the algorithm. Because if it takes you 7 guesses to pick a number between 0 and 100, what does it take between 0 and 1,000? It takes 10 guesses. It's a few more. And 0 to 1,000,000,000, it's 30 guesses. Alright, so this is very efficient. This is more common. N times log n. It's not as bad as n squared, but it's worse than log n. This is the one you really don't want. Order n to the n. That's traveling salesperson, CSE215 topic. Okay. What's the best order of efficiency we could hope for? Well, I mean, the absolute best would be order 0. That would be an algorithm that takes no time, no matter how big your problem is. And that's either completely impossible or that's everything, because time is an illusion. But the best practical order of complexity we can get is order 1. Order 1 says, yeah, exactly, says your algorithm always takes the same amount of time, no matter how big the problem is. So if it takes, you know, a millisecond for 10 pieces of data, it'll take a millisecond for 10 trillion pieces of data. Right? In other words, the time is independent of the size of the problem. And order 1, that's the complexity of an associative array. For either writing something into an array or retrieving from an array, theoretically, it's a fixed amount of time no matter how much stuff is in the array. And that's the magic of associative arrays, right? Also called hashes. So we'll learn how that works. We'll code this up in C next quarter, and then we'll use it a lot in 223 in spring, using some Java classes to play with these things. But it's really extremely efficient. But when we run a bash program to index Wuthering Heights, you know, which is 600,000 characters, it's the fact that bash is interpreted, and we're going through a lot of lines of code inside our inner for loop, inside an outer while loop. That's what's taking up the time, right? It's not actually the associative array. And if you played around with a different version of this that does something like, you know, just sort your input and run it through unique-c, that's so much faster because those commands, sort and unique and awk and all of that, those are C programs. Those are running, you know, as executable code. They're not being interpreted. And so that's where the speed comes from. Yay, yeah, it's good when your system doesn't crash. Yeah, so an associative array is really just a hash, and when you store a phrase in that array, that phrase gets run through a hash function of some sort, and that basically tells it where it should find this phrase if it's in the array. Then you just go right to that location. You either find the array or the key, or you don't. So they're fairly magical. All right, so any other questions, comments on homework 8? All right, so we played with with the system command last week, I'm pretty sure. Basically, you can say system and put a command in. And, you know, you can do this in your C program, and when your C program runs, it will execute that command. Right? So that's useful. If you want to do something like, you know, send an email in the middle of your C program, you can run the mail client, right? The limitation of this, though, is that this command runs in its own shell, and your C program kind of goes on hold while this new thing is running. So, so let me do some stuff here. Right, so let's just call a system command echo and say echo hello. Right, so we run P10 and it says hello. Well, that's not terribly exciting, right? But we could do something like, you know, read you know, let's do a read -p, which prints out a prompt and asks the person for a password. Right, so I run this and it says password, and I can type in my password, right? And if we look at the return from the system command, right, to see what we get back from executing this. So I put in my password as hello. My status comes back as a 0. Let's see. Did it give the correct output or just run? Is that a question about this? Ah, okay. Yeah, well, not crashing is like half the challenge, right? So this return value from system does not tell us the result of this command in the sense that, you know, we read something from the user. We don't have access to that through this return value. So in fact, system always returns a 0 if our command succeeds, and if our command fails, it gives us back a non-zero value. In this case, 32,512, which happens to be 127 times 256, and there's reasons for that. If we give it something like, you know, a valid command, but a command that cannot succeed because there's no file with this name in my directory, then it gives me an error code of 256. So the main thing with the call to system is if it succeeds, it will give us a 0 back, typically, but it gives us the return value from whatever command we executed. Okay? If it gives us a non-zero status, something went wrong, and it could be that the command wasn't able to run, it could be the command wasn't found, or it could be something went wrong with system, like somebody fork bombed the system and there were no process slots available, and system could not create a process to execute this command. So we generally check the status of it. And so let's just look at a PS, and this kind of gives you the whole story here. Here's my bash shell. this created a command to execute P10, which happened right here when I said P10. P10 created a new process which executed the command sh-c ps-lf. So the call to system creates a new process to execute the command sh-c, whatever command you specify in the system call. And that's a shell. It's like bash, but it's just called sh. And that process created a new process to execute the command ps-lf. So 3 levels of processes happened when I said P10. And now, you know, those are all gone. And this is a different PSLF that I just did from bash. Alright, so takeaway message from this, right? This is a really useful way to run a command if you just want to run a command, but it's not useful for interacting with that command from C. Okay, now I can do something like, you know, execute the command BC, which is our calculator, and I can say, you know, what's 2 plus 2, what's 5 times 8, and so on. Right? But none of that information is available to my C program. So this is really just saying, you know, go off and run this command and then come back when you're done. Tell me if the command succeeded. So what we would like to do is be able to do something like, you know, calculate large powers of 2, which BC will do for us very easily. Eventually. Ooh, I stumped BC. Ooh, dang. That's weird. So you can calculate large powers of 2 with BC, just not too large. But certainly bigger than what we can do from a C program. Right? If we wanted to calculate the value of this exponent in C, we'd have to, you know, write some code to do decimal arithmetic and so on and so forth. So it would be nice if we could get BC to do this for us. Right? So this is what we're working towards. Something where we have a C program which starts executing and creates a new process, such as BC, but then sends input to standard in of that command. Okay, or a C program that creates a new process but can take standard out and send that back to our C program so we can read the result of executing some large arithmetic operation. In other words, we want to be able to do more from C than just say, run a program, let me know when you're done. We want to interact with that program while it's running, either sending some information to it or getting some information back from it. And that's going to be really easy to do using a command called popen. And popen is almost like system, except in addition to running a command in a new process, it also gives us a conduit for talking to that process. Right? So this is a chapter 3 function, just like system. It's still pretty high level. Alright? Before we can really work with popen, though, we need to understand how we interact with files. So I want to go back and do a refresher on file IO. And in particular, I want to look at fopen, fclose, fgets, fprintf, and fflush. So you've seen these in 121, or at least most of these in 121, but But the things we do for reading from or writing to a file are the same things we're going to do for reading from or writing to a process using popen. Okay, so I want to review this with files first. So this is most likely stuff you've seen before. All right, so so here's the thing. We're going to open a file. So we're going to say fopen. We'll call it cool file. Okay. We want to open this file. We want to read its contents into our C program. So we know how to read from standard in, and we know how to run a program and redirect standard in on the command line. But now I want to do something different. Inside my C code, I just want to read from this file without having to say, you know, run this program redirected from cool file. All right. So we have to open the file, right? So fopen opens it up, and we have to say, what are we going to do with it? Are we going to read or are we going to write? So we put a second argument on here, which is R for read. So that opens it for reading. And even though just calling fopen will open the file, we can't do anything with the file unless we have some way of getting to its contents. So fopen opens the file, but more importantly, it returns what we can call a handle to that file. Okay, something called a file pointer. And the type of thing it returns is this pointer to a variable of type uppercase file. So here, if we say fp equals, now fp gives us access to that file. So let's call fgets. And let's do 120 characters into a temporary buffer. And this third argument to fgets, that's what you want to read from. Normally this is standard in. We're just going to make it equal to fp, because that's what we're reading from. So I'm going to put a message here and say calling fgets. And I'm going to put a message here and say I'm back from fgets. And I'm going to print out the value of temp. Alright, so this is test code. And while we're at it, I'm going to print out fp up here. And I'm going to print it out as a %p because I know it's a pointer. So previous section I printed it out as an integer just so we could look at it. But I'll print it out as a pointer, right? So we can see what that is. And let's put a message up here. And we'll say about to call fopen. Alright, so there's P11. I knew I'd get some errors anyway. Alright, how's that look? Yay. Alright, so let's go ahead and run this. Alright. But call fopen, and then it calls it, and it tells me fp is equal to nil. And then it says calling fgets, and I got a segmentation fault. Alright, this is what was supposed to happen. So let's take a look at fopen. And, you know, we took the return value, we stated in fp, fp came out to be nil. Nil is null, it means it's a 0. So let's look at the manual page for fopen, right? Still a chapter 3 function. And let's go down to the bottom where it says return value. And upon successful completion, these return a file pointer, otherwise null is returned. All right. Since it returned null or nil, which is how %p prints it, there is a problem. And most of these functions in C, they also set this global variable called errno. It's a variable that gets set to an integer that corresponds to what the actual error was. And then there's functions we can call that will interpret this errno value and give us a human readable piece of information telling us what went wrong. So what went wrong in this case is really straightforward. I don't have a file called cool file in my directory. Alright, so we'll fix that in a second. Let me mention something else in here though. And I saw this popping up in homework 8. When you're putting debug statements in your code, try to make them as usable as possible. For example, I put a message saying about to call fopen, and then I called fopen, then I printed out fp. And then I said calling fgets, called fgets, and then I said I'm back from fgets, and then I tried to print out the value of temp, right? And so it was really clear when I ran this what happened and where things died. I called fopen, I came back, fp was that, I was about to call fgets, that's when I got my seg fault. So that tells me right now, I know, absolutely guaranteed, this was where my seg fault occurred. So put you know, stuff in the beginning of your print messages, let yourself know what it is you're printing out. Right, so you know, homework 8, I'd help people and they're modifying their line, you know, their line of input in 10 different statements, and they just keep echoing it each time. Well, how do you know which line of output corresponds to which line of your program? Right, you got to go back and you got to count and compare and match up and stuff like that. Make life easier on yourself, right? So be explicit. Let me mention one other thing in here. Put new lines at the end of your print statements. Yeah, -x is really helpful for bash too. Right? Suppose I don't put a new line in there. I want to say calling fgets colon, and then I'll say back from fgets. Well, when I run this, it says about to call fopen, fp equals nil, and then I got a seg fault. Right? So about to call fopen, fp is nil, and the next thing was a segmentation fault. Well, if I look at my code, about to call fopen, I printed out fp, and then I got a seg fault. It never printed out calling fgets. So that can look really confusing, right? Because it must not have even gotten to this statement. It got a seg fault somewhere between here and here, right? Well, this is where the new line comes from, right? By putting a new line on, you force this output to appear immediately. Remember, when we print things, print statements don't always happen as soon as you say printf. Sometimes they get saved up and pushed out later on. So always put a new line after debug messages. Now it's really clear we're calling fgets, and that's where the seg fault occurs. Okay, why do we get a seg fault? Because there's no file in here called cool file. So let's make a file, cool file. Alright, so there's my cool file with some typos. And now I run my program, called fgets, came back from fgets. My fp was not nil anymore. It's got a nice, you know, memory looking address. And fgets returned, and my value of my temp string was this first line of my file with a new line at the end. Oh, there you go, okay. I was about to say that. Alright, so if we want to read multiple things from our file, we can make a loop. So let me clear out some of these debug statements. And fgets, look at the return value, returns your pointer to your buffer on success or null on an error or when the end of file occurs. So this is the same fgets that we've been using when we read from standard in. So we can put this in a loop. So something like, well, null is not equal to fgets. Let's print out the value of that buffer. Right, so now it reads my file one line at a time, prints it out, gets to the end of the file, detects the OF, and the while loop exits. Alright, the other thing is if we want to write to a file, we say quote W. So I'm going to clear out my debug statements. And I'll write some stuff out to my file. And I'll run that. And now if I look at cool file, it's got that one line that I just wrote into it. Right, if I write that line out 20 times in a for loop, right, cool file has 20 lines of output in it. So that's all there is to doing file I/O. Right, so fopen lets us create a file or open an existing file, and we have our last argument, which is either read or write. We can do other things. We can do append. We can open for read with appending, and so on and so forth. But those are our first two. Fgets reads from a file. Fprintf writes to a file. The two we haven't talked about are fclose and fflush. I talk about those at the end of the previous section's lecture. You can look at those if you're curious, but we'll come back to them when we talk about pipes tomorrow. But basically, always call fclose when you're done. That frees up any resources that are being used for the file I/O, but it also forces all of the stuff you've written to the file to actually go out to the file. And remember, if you write something and you don't put a new line at the end, it may not appear right away. And in writing to files, even with a new line, your output may not go into the file right away. And the buzzword, if you're interested in there, is buffered I/O. So closing always flushes your buffer, but you can also call this function fflush to force the buffer to get written out immediately. And we'll play with this more when we deal with pipes tomorrow, and then when we talk about making processes from a low level next week. All right, so that's our basic setup. Tomorrow we'll go ahead and we'll use this with popen to execute a Unix command and be able to interact with it a little bit, one directionally. And then we'll see how to do bidirectional communication with a process, and that will give us our whole chain that we need for working with processes. Yes, so when your program exits, any files you have open get closed, any resources you have in use get freed up. So if you're going to do something like this, right, when my program exits, it's good. Everything gets written out to file, everything gets flushed and closed, and so on. But if I do something like, you know, sleep for 60 seconds at the end, and let's run this in the background. If I look at cool file, it has nothing in it. Even though, you know, I've already looped and I've written hello world 20 times into this file, my cool file is empty. And the reason it's empty is because it's inefficient to write to a file. Right? File I/O is really expensive. This gets into other conversations, but the system tries to save up all of your writes and then push them all out at once, either because it's got enough stuff to make it worthwhile to write it to the file, or because you exit the program, or you call fclose, or you call fflush. So eventually 60 seconds pass, and we look at cool file, and you know our program will have exited, and all of this will get flushed out. 60 seconds. There we go. All right. So F flush and F close just let us force whatever we've written to actually get sent out to the device. All right, cool. I will see you next time. We'll talk about popen and working with piped processes tomorrow. Have a good one. Catch you next time. Thanks.